So you have a third double integrals homework due tonight at 5. I looked. You guys seem to be doing fine on that. The success rate on all the problems was high. So we're going to press on. And then, yeah, we're just on normal track now. Homework's due, written homework's due Thursday nights. Web works every class. So we're cruising along here. So let's review and talk about, and then, so here is, I got a region D, I got a surface, Z equals a multivariable surface f of x, y, and I want you to recall and practice, what does the double integral of f over region D? So that's what we would call this right here. We'd say this is the double integral of f over D, right? Double integral of f over D. And we've talked about two different contexts, right? We've talked about the kind of rate of change accumulation context. We've also talked about geometry context. So see if you can think about that. Maybe have a short conversation. And when you talk about what these represent, you want to include all the details, right? All the nitty-gritty details of what exactly you're talking about. So to just say, it's temperature. That doesn't include any details. Like, what temperature is it? Over what time period? In what space? So like, when you say in general what it represents, be specific. Give all the details. Okay. So think about that, and then share with the person next to you. So just good morning. This is the 4th day in a row we've talked about this. 4th day. 4th fast time.
Rate and accumulation. For geometry, this is the volume under the curve. It's the sign volume under the curve. Volume over the negative.
Okay. So, Eric and Cody, what did you guys, for rate and accumulation, what did you say this meant in the context of rate and accumulation?
Context of rate accumulation, the double integral represents the sign volume over the region D.
That's geometry. Sign volume, that's geometry.
Then the rate of change, the f of x, y is the rate of change of x and y over the region D, and you accumulate whatever your unit is going to end up being.
Yep.
For that particular region.
Okay. And so what does the whole thing, if this is the rate of change of a multivariable rate of change, right, a rate with respect to two different things changing, what does that value of that double integral, what does it compute? Yeah, like total accumulation of a quantity, right, whose multivariable rate is f, right? So it's the net accumulation, right? Net accumulation of some quantity whose multivariable rate is f. Okay? What about geometry? Samantha, what did you think about geometry?
It'll give you the sign volume under the curve But in this case, it's just absolute volume because the function, the rate of change function is positive.
Okay, so sine volume under.
So the region in the XY plane projected onto the multivariable function.
Okay. So sine volume, is it always under? It's always under? So what could we say to make it more general? So in this case, it would be under, right? But in general, it would be sine volume. What could we say? Between, right? Between what? Okay, you guys, everyone keeps saying curve. Curve, surface, and XY plane. Yeah, so if you define the region as in the XY plane, then yeah, and the XY plane. Okay, any other details to the sine volume? Okay, so sine volume is difference of volumes. But in terms of that solid, forming that solid, there's still, we've got the kind of, if it's between the surface and the XY plane, that's kind of like the top and bottom, right? So what defines the sides? Right, so the vertical sides are like the cylinder formed by D, right? Like the cylinder formed by the edges of D. So here's a very formal way to say it, or it's the sine volume of the solid formed between F and the XY plane within the vertical cylinder defined by D's boundary. So that's like an A++ definition. It's kind of, and this would be kind of like solids, right? So if we're sometimes above, if F is sometimes above and sometimes below, then we're actually going to get solids, right? We're going to get the solids, some solids above, some solids below. Okay, that's review. And that's the fourth class in a row that we've gone over what a double integral gives, right? So it's going to be 100% on that question on the test, right? Not 40, 50, 60% as in past semesters. 100%, right? Fourth time in a row that we've gone over that. Okay? Everyone get it right on the test, okay? So let's take this a step further then. So suppose that f is a positive constant function, z equals k. So now I'm saying it's a constant surface, right? Constant function. Then what would the double integral give? What volume? Be more specific. So how could you write that volume now without a double integral? Yeah.
The area of D times K.
Area of D times K, he said. Agree with that? Yes, this is a solid cylinder, so the area of the base times the height. So it'd be the area of D times K, right? So the area of D times K, exactly what he said. All right. So then, if that's true, if the double integral, if f is a constant function, and the double integral would then give the volume of the right cylinder, area of D times K, how could we use a double integral to express the area of D? How could we, looking at this right here, everyone think about this. How could we use a double integral to find the area of D?
Or double integral divided by a constant k.
No, I'm not asking you to solve both sides for area of D. I want the double integral to compute. I want to compute a double integral, and I want it to give me the area of D. What do we do to do that? These guys know. These guys know. How about in the back? What should I do if I want the double integral to be the just plain old the area of D? What is it now? If it's a constant function, it's area of D times K. So what could I do? So the double integral just gives me area of D. What's that? No, I'm not asking you to solve for. I'm not asking you to solve for D, right? I'm saying I want to compute a double integral and I want it to give me the area of D. What should I do to do that? Yeah.
Let K equal 1.
Yeah, and that's what Jeff said too. Make K equals 1, right? Make K equal 1. And so what does that mean? What does that mean that we're integrating that? If K equals 1, then what is my double integral? Then the value of the function is 1, right? I'm going to do a constant function of 1. So in general, what do double integrals find? What do they find? Geometry? Sine volume. But we can trick it to get us the area for us, right? How do we trick it to get us the area for us? The area of D. Make the function 1. If you make the function 1, then you're finding the volume of a right cylinder whose height is 1. And that volume will be the same as the area of D. Does that make sense? Did you follow all that? It's a really important concept.
Just in square it rather than cubic units. Like the area.
It will still be cubic units.
Right.
It'll still be cubic units, but the value of it will be the
Right,
same
right.
as the area of the base. That's right. It'll still be cubic units, but because it's finding sine volume, right? It's still finding sine volume, but we know that the value of that sine volume is going to be the same as the area of D. Does it make sense? Really important idea here. Questions? Okay, so going back to our last example from last time. This one. We did this, and we got that. So first of all, how do we do this? We drew the region, right? These changing the limits of integration are geometry problems, right? They're geometry problems. And we drew this thing. It's better, okay. And so we drew this out, and this represented the double integral of f over that region there, and then we rewrote the limits. And I think when we rewrote the limits, we got this here at the end of class. So the question is, I want to know what the area of that is. So if this is region D, what's the area of D? How would I find the area of D? What's that? Right, let f of x, y equal 1. So here's the original integral. So right here, my integrand will be 1. So I get area of 13.8394. And then here's the rewritten version. Right, here's the rewritten version. What should I do? 1 again. 1 and... you're killing me. Why doesn't I made a mistake somewhere? dy dx, dy dx. Oh, no, that's right. That should be y. Is this one? No, that's right. Did I make a mistake anywhere? No. So there's some keystroke typing thing that I've did, but I think that that's what we came up with last time. And that will give the exact same value. That will give 13.8394. For whatever reason it's not, but it should. If I went and retyped the whole thing, it would work. There's some space or some weird extra keystroke that we can't see. Doesn't make sense. So this would be 3.8394 as well. And that's what you're doing in your homework. You're practicing lots of rewriting these double integrals in the other order, and you're rewriting the same value in another form, right? Now, if this is not 1, then you're no longer finding area. You're always finding sine volume, right? You're always finding sine volume. You're also finding the area of D if your function is 1. Okay, so there's still another way we can do this one. So looking at this here. So do you remember anything from Calc 2 that might apply for this particular region here? Does that look familiar? It's kind of... Yeah? Anyone else see it? What is this from Calc 2? Polar coordinates? Does it look like polar coordinates? What are polar coordinates? That's right. So polar coordinates. Points are defined as r comma theta. But this is kind of backwards the way we think about it. We think about theta as independent in polar coordinates, right? And r as dependent. So often most of the time it's r as a function of theta. But when we list the points, we put r first. So it's backwards to what we're used to. So what have we been doing? We've been saying things like, our tiers have been like left to right, bottom to top, or bottom to top, left to right. So what was this? It was given as what? Left to right, bottom to top, or type 2. Left to right, and then bottom to top. Then we summed up all those. That's how it was given, right? As a type 2. So in polar coordinates, and then we rewrote it in as the sum of 2 vectors, and that was, or sum of 2 double integrals, and that was bottom to top and left to right. But our top was different, right? So our top was broken up into two pieces, and so we needed 2 double integrals because the top was different for different values of x. Okay, so what would the cheer be for polar coordinates? What would the cheer be for polar coordinates if our coordinates are r and theta? What's that?
Inside out, turn around.
Kinda, not turn around. But he said, so first of all, he said inside out. So are you referring to r or theta there?
For R.
R, right? So for r, it's going to be like we're going to go from the least radius to the greatest radius. So he said like inside out. That's right. Like so inside out. And then what about theta? Right. So I heard sweep and I heard counterclockwise. That's right. So inside to out, and then like so lower value of theta to higher value of theta. So it'd be like a sweep, a counterclockwise sweep. So lower theta to higher theta, which would be a counterclockwise sweep. Okay, so we'll just hold on to this for a second here, and let's talk theory here. So that's going to be the general idea of polar coordinates, that our double integrals in polar coordinates are going to be from inside to out, or lowest value of r to greatest value of r. So from the origin, increasing away from the origin, and then lower theta to higher theta, which is going to be a counterclockwise sweep, right? Because our angle theta increases counterclockwise from the x-axis. Let's look at this here. So here's the general version of that. This blue one, this is one function of theta. R is a function of theta. And then the red one is a second. R is a function of theta. And then it's going to be from starting angle theta, sweeping counterclockwise to a finishing angle theta. I've got alpha and beta. So yeah, so inside to outside, theta 1 to theta 2 is going to be our cheer for polar double integrals. So if we were to write a general form of polar double integral, what would it look like? What would be my first limits of integration here? Right, so it's going to be, if inside to outside, that's r's first. It's going to be h1 of theta 2, h2 of theta, and then, so it's going to be, that's going to be dr, and then d theta. Theta goes from theta 1 to theta 2. No, we won't have reversing the order of integration, right? Because this is writing theta as a function of r it's not nice, okay? So we're always going to do radius first. The order will always be radius and then angle. So the question is, so we have some function. So if our function is a function of x and y, does that just become f of r theta? What is x? What is x in polar coordinates? What is our x value? R cosine theta, right? Some people are saying it. And then? Yeah, so if we're transferring from x and y to, if our function is given in x and y, then everywhere there's an x, that's now r cosine theta. And everywhere there's a y, that's going to be r sine theta. You can't just exchange x and y for r and theta. You have to do the right mathematical exchange, right? Okay, so the question is that dA, right? So our dx dy, we know that's like a little rectangle, right? Dx dy is a little rectangle, and that gives us our dA. So what about dr d theta? Does that give dA? No. So no, because theta is not a length, right? Theta is not length. Theta is angle. So d theta is a change in angle. So we're going to start by filling in the blanks here. We're going to figure out, we need to figure out what dA is. All right, so what can we fill in the blanks here? Let's see. Let's start with this right here. What would that be? If this is our dA, this little purple sector thing, what would that be right there? But if this is dA, someone said it, this is d theta. This is the little change in angle associated with our little element. So then what is this angle from the x-axis? From here to here. That's just our theta. So this d theta, think of this as really small, right? D theta is a really small sliver of change in angle. And it occurs at some angle theta. Okay, what about, let's go with this right here. So what would this be? That's dr. And this is, so from the origin out to our elements would be
Just R.
r. So the question is, what is this, right? So dA is just going to be this unknown times dr. So we're going to treat it as a rectangle. But this dimension is not d theta, right? This dimension is not d theta because why? Because that dimension down here would be small. And the further you get away, it gets larger and larger, right?
R times d theta.
Right, so from a circular arc length, let's say you have an angle alpha like this, what arc length does alpha cut off? Right, so this arc length, S, is the angle measured in radians times the radius. Arc length is proportional to radius and angle measure. So this is where angle measure comes from, right? This is where the radian angle measure comes from. It's the ratio of S to R. So then S is alpha times R, which makes our unknown dimension here what? This is going to be R d theta. And so now we have what dA is. Just treating it as a rectangle, it's like base times height. So it's going to be R d theta times R dr. So remember, so the key is that d theta is not length, right? D theta is not length. It's like openness, right? It's like a little bit of openness. So to get length, you have to know how far away from the origin you are, and that's, you just multiply your radius times openness, and that gives you the length of that element. Make sense? Any questions? So therefore, this is not dA, but what is dA instead? R dr d theta, right? Okay, so what happens to the R? So we've got our, then our double integral is this. Well, let me just, instead of writing the whole thing again, we've basically got it written up there, so I'll just, that's a single integral. So what's the relationship between that? Right? So now this is a double integral. Okay, so the dA is the R dr d theta, but what happens to the R, right? So this is all multiplied, right? So it's still, to find dA, we multiplied, right? And now we're multiplying dA by our function. So what happens to the R? This is everything multiplied together, right? So we've got the function written in terms of R and theta times R times dr times d theta. So what happens to the R? It's just all multiplied. So it just attaches to the function, right? It just puts another R on our function, right? So it comes to the party with the dr d theta, then it goes home with the f function. Okay. So what we have to get good at first is, before we actually start solving these, is just identifying given regions, what are the limits, right? Given regions, what are the corresponding limits? So let's practice that. and I'll take attendance. So here's some regions. And so all you're doing here is just the limits of integration, right? So what would we have? We'd have some surface in R3 over these regions, right? Some multivariable function surface. But now we're just looking at the xy plane, just like before. We're looking at the polar plane, and we're figuring out what these are our regions D. So D1, D2, D3, D4. And we know that the region pertains to the limits of integration. So we're just practicing writing the limits of integration in polar coordinates. Okay, so all the, these are all units, right? So this is 1, 2, 3, like this. 1. And all of the graphs are the same way, like that. And then all of the angles are multiples of pi over 4. Okay, David, did you get the first one? Did you get this first one? 0 to 2? You want 0 to 2, 0 to 5 pi over 4. And then we have F, R, d, r, d theta. Agree? Okay. Lily, did you get this next one? Okay. Yep, sure. How'd she do? Okay, and then let's see here. Elizabeth. Okay, so it's 0 to 2. So you start with the bottom. So we go from 0 to 2, just like the cheer, right? Inside to outside. Okay, and then pi. Good. Agree? Jacob, did you get the last one?
Yeah. The inner I got from 2 to 3.
From 2 to 3, good.
And then the outer I got from negative pi force to 3 pi force.
Is this making sense to everybody? Okay, and then, all right, so let's go back to the one that we did, and let's, so I want you to write that one, number 4. Any questions on these before we move on? And I erase? Good? Let's go back to I'm in the right place. Let's go back to this one. And I want you to write that as a polar double integral. So we made the picture. R goes from what to what? That's the easy part, right? So now the question is, what are our limits on the angle?
The sine inverse of angle.
So it's going to go from, what's our lower angle? 0. Theta equals 0. It's just the x-axis. Okay, so then what angle corresponds to y equals 2x? So how do we get an angle out of that? How do we get an angle out of that? What's the slope? 2. And how can we get from slope to angle? Inverse tangent, right? Inverse tangent. So let's see if it works. So from 0 to Inverse tangent of 2. Now, I want this to show, now, I want the double integral to give me the area. What should I put in the question mark? I want it to give me area. 1? Not right.
Is the question mark where R is supposed to be? I can't tell from back here.
It's where the integrand is supposed to be. What should we integrate to get area? R, right? Because it's 1 times dA, but what's dA in polar coordinates? R dr d theta, not just dr d theta. So hopefully this will work. It worked. See? So the integrand becomes R because this whole thing is dA. And it still is 1 times dA, but you need the whole dA in polar coordinates, which is R dr d theta. And so then R becomes your integrand. Does that make sense? Okay, so let's do another example. Questions on this one? So really, what's the most efficient way to do this one? This particular double integral. Yeah, polar. It's really the most aligned or suited to polar coordinates because it's a constant r and constant theta. Constant theta is in constant r. If we do it in x and y, we're writing circles in x and y, which involves square roots, and we've got functions. But this is a super easy double integrals with all constant limits of integration, right? Constant r and constant angle. Okay. 0 to 5, 0 to arctangent of 2. So it's really the most efficient in polar coordinates because of the region is suited best to polar coordinates. But all 3 will give the same value. Okay, so another example. Somewhere here, this one. Okay, so the first thing you're going to do, this is a, type 1 double integral. I want you to sketch the region in the xy plane. Let's skip over 2 for time's sake. We'll come back and do 2 if we have time at the end, but let's just do 1 and 3. We're going to sketch the region in the xy plane, and then I want you to change the integral to polar coordinates. So R goes from inside to outside. R goes from 0 to 4, right? 0 to 4. At any given angle, you start at 0 out to 4, right? And then theta goes from pi halves. Starting angle is straight up. That's pi halves to 3 pi over 2. And now we got to change this, right? So x is? Okay, now before we start plugging in r cosine theta and r sine theta, what is x squared plus y squared in polar coordinates? R squared, right? So the denominator is r. dy dx is? R dr d theta. So the r comes with the dr d theta, but then it latches on to the function, and what happens? That can in this particular problem that can become 1. So then we're integrating r cosine theta dr d theta from 0 to 4. The way it's given type 1, you can't even really make, that's a difficult, if not impossible, integral with respect to y, the first. So if you change the order to x, you can do it. You can actually do it, but this is still a whole lot easier, right? Because this is a polar region. This is a polar region, so your polar double integral will be the easiest.